PaulGradenwitz says that we have a lambda CDM model that describes the universe as expanding. Actually, in the graph of proper distance versus time, we have the particles moving away from each other. And in the graph of comoving distance versus time, we have the particles sticking together. Or no, not expanding. Comoving distance. In the comoving distance version, the universe is not expanding. My understanding is this the scale factor, the scale of the universe, is a relationship between the comoving distance and the proper distance. So for instance, looking at t equals 5 on this chart, it's going to be the distance between, say, that, let's do the z equals 1 particles at 5 from there to there, the z equals 1. And I don't know if it completely gets on that line, but we'll do the z equals 1 up here. Here's the 1, and at 5, we'll do from there to there. Now, later on, we are at z equals 10, and the z equals 1 particles are still just exactly the same distance apart. So z equals 1 up here, we have that. So the ratio, the scale factor ratio, has gone from this level to this level. So A of t is changing. The amount that the scale factor is changing. But in this graph, things have been stretched. So we've got this thing change from, say, well, it's constant here too. Scale factor. Scale factor does not change between these two graphs, but it does change between these two graphs. So there's something else that's been scaled between these two graphs. It's the scale of time. Let's look at some feature of these two graphs that is the same. Say this element here and this element here. Between the Hubble sphere and between the crossing of the z equals 1 particles across the Hubble sphere, and then their next crossing across the light cone. So we're going to draw that on this diagram because we've got the Hubble sphere and the light cone there. Nope, that's the light cone. I'm sorry, I've drawn this really small, but so small I can't actually read it, but I just wanted to get everything on the screen at the same time. So here is a scaling in the z direction because this is time, this is conformal time. Basically this has been revamped to make this thing taller. So this is a scaling in time, this thing is a scaling in space. So let me come back to a previous reply of PaulGradenwitz, which talks about these things. L of z, let's write it L of z over L sub naught equals 1 plus z, and T of z over T sub naught equals 1 plus z. Now I feel like that if we are changing from time to T sub naught, this can kind of refer to this graph because it is a change in the time scale down here to the time scale up here. This one, on the other hand, is kind of a transition between this and this because this is affecting a length scale right here to a length scale right here, I think. So that is affecting a length of things. I think what length is being held constant here is this one, the length now. So those two lines, if I'm not mistaken, should be line up exactly. And then this should match up with that crossing there. This should match up with that crossing there. So this has, on this line, everything is exactly the same. But on the lines below, we're going to be affecting things with some kind of equation here. Now my feeling is, if this is actually intended to express a model of the universe, then one of these pictures should be the Euclidean space and uh, the time that we actually like measure. Um, if any of these are supposed to be um, the actual space, I feel like the one with the most promise, if I mean, not that I actually like give this model, I really expect this model to be reality, but it's just that this version of it makes some sense to me if, it's really the only version of it that makes any sense to me at all, that could be even remotely close to what we observe, is if time was literally going slower at this point than it was here. If time was going, you know, if the time between events was going slower along this line than it is here, then it would serve to it would stand to reason that a particle emitting something right here, because that's the pass light cone, would have a time on it, and that would it would or the frequency of the photon released would be a little bit lower, say. But then the wavelength of that photon is going to be just the speed of light over its frequency. And so when that wavelength gets here, and that frequency is going to be basically f sub naught times this fraction. It's going to be a slower frequency. Yeah, it's going to be a slower frequency. So it's f sub naught over 1 plus z, which is the same as f sub naught times t of z, the speed of time here divided by t sub naught. T of z, the speed of time then divided by the speed of time now. And then you don't have to actually apply this formula to go from here to here. What you do is you actually derive something about lambda at that place z divided by lambda sub naught, which is going to also end up being, which is this is actually lambda of z here, c over f sub naught times c over f sub naught over 1 plus z. That's kind of a divided by c over f sub naught, which is going to be 1 plus z. So, so you can actually derive this about the wavelength just between this map and this map, assuming that this quality about wavelengths and frequencies is accurate. You don't need to then make another statement stating that L of z over L sub naught equals 1 plus z, which takes you into another coordinate system. Now there might be a similar argument that goes from this one to this one and says this is earlier my argument was essentially that this one is Euclidean and this is sort of and this one has the conformal time marching forward at a sort of regular rate. Well, it's the space where the speed of light is constant, and that works well. That one works well with frequency times wavelength equals the speed of light, because I feel like that's where we can use that equation in a situation where the speed of light is constant. If we make this the Euclidean time, though, then we're going to have the problem that f lambda, I don't think we can make that claim that f lambda is equal to c, because the speed of light in this situation is doing this weird thing where um, this this light cone is actually coming toward us, but on this graph it's going away from us until a certain time where it crosses, I don't know, the Hubble sphere and then comes back. It's weird. So I don't think we can apply the f lambda equals c to get to there in that direction. It only works in this direction. So do we have the LCDM that describes the universe as expanding? Well, it depends on where you're looking. In this diagram, the universe is expanding, because these dotted lines representing uh, particles of constant z equals 1, 3, 10, 1,000, or whatever, those are moving outward over time. Um, I, but we also have this weird thing going on with a light cone where this inward coming light cone is also represented as moving outward at the beginning, which is weird because it's coming inward and is represented as outward. Here it's not so weird because the inward coming light cone is coming inward, which makes a lot more sense. And here we have the inward coming light cone coming inward at a constant speed, which seems consistent with special relativity. If these are Euclidean coordinates, then it is consistent with relativity, except for the fact that I think we've kind of we've thrown away special relativity by the time we get to this graph. But I think really what we have to do is we have to choose a paradigm. We have to decide, does this represent the Euclidean coordinates, or does this represent the Euclidean coordinates? And if the top graph represents the Euclidean coordinates, then we will use something along the line of L of z over L sub naught equals 1 plus z. And if the bottom graph represents the Euclidean coordinates, we would have t of z over t sub naught equals 1 plus z. I might have that mixed up. I'm not sure looking at it. If one of these is the Euclidean coordinates, then we'd have this represent our something. Or maybe it's the center one represents the Euclidean, and this transformation puts you there, and this transformation puts you up there. So, except for the fact that this is a linear transformation. This here is a linear transformation. All it does, no, it's not. It's not a linear transformation. But what it does is it stretches each portion of the graph by a slightly different amount. So where this is sloped a lot, where this is almost horizontal, it's got to stretch that bottom part of the graph a lot. But where it's not horizontal, it only stretches it a little bit. It doesn't stretch it at all here, but it stretches it more and more and more as you go down, until actually the bottom of the graph, the very bottom of the graph here, is being stretched like infinitely. But with that one, the variation is stretching in the same way as the other thing. This one, it stretches this part more, and then it stretches this part a little bit less, and it stretches this part a little bit less, and it stretches that not at all. And so it ends up being so it ends up having the stretch factor being perpendicular to the coordinate by which that stretch factor is being chosen. So that I'm not sure if whether this equation is going to work for that the same way as this one or not. So that's involving the LCDM, and that's pretty confusing just with that. So actually, I think, having thought about it a little bit, I want to say this one is Euclidean, or this one needs to be Euclidean. So thinking about it in this perspective, the speed of light is slowing down. See down here in this first part where the light cone is spread out really far, that is an infinite speed of light. And then the speed of light is slowing down. Now here it's equal to about 3 times 10 to the 8th meters per second. And it's getting slower and slower over time. But in this graph, the speed of light is actually constant over that time. But here, time is going slower, time is getting faster as time goes by. So that's why distant objects, an object here with z equals 1000, z plus 1 is 1001. So a particle here emitting sends an extremely low frequency wave going here at the speed of light to us. I guess we would receive that now. Oh, I'm on the wrong light cone. Should be on this one. So we're receiving that information now from a very low frequency, what would be a normal frequency then, but because the speed of light is low, ends up being a low frequency. But we observe that time as though the time is ticked in an ordinary fashion. So yeah. So in this interpretation of it, the speed of light was faster down here than it is now. But actually this has Euclidean space, but C is not preserved. But the rate of time, delta t, I don't know how to say that. The delta t over delta t, delta t of the clock per delta t experienced is constant. So C is not constant in this graph. The time scale is constant. But in this one, the actual, this t is changing. But they've got it labeled by scale factor, but they really should be, this should be, in this graph, it would make sense to mark this by a time scale factor. All right, well, we'll see how this records. Thanks for watching.